One important law dealing with how charges interact with each other is called Coulomb's law. In this video, what we're going to cover is what is Coulomb's law in the first place. We're going to look at how we can calculate an electric force using Coulomb's law, and also finding a resulting force acting on a charge due to two or more charged particles. I'm going to have you watch a video clip that was actually created by another teacher, but it does a really good job of explaining what Coulomb's law is.
If two objects have electrical charges Q1 and Q2, and if they're separated by a distance r, then Coulomb's law says that the electrical or Coulombic force between these objects is kQ1Q2 over r squared. K, which you write here as K sub E, E for electrical, is a constant, approximately equal to 9 times 10 to the 9 Newton meter squared per Coulomb squared. Now, matter can be electrically charged. Charges can be positive, negative, or neutral. If an object is neutral, it has zero electrical charge. Here's the representation we'll use for a positive charge, a negative charge, and a neutral charge. Coulomb's law says that like charges, that is, charges with the same sign, repel each other, while opposite charges attract. If we put two positive charges close together, they'll repel each other since they have the same sign. The same goes for two negative charges. If a positive and a negative charge are near each other, they'll attract. And neutral charges won't interact with electrically charged objects. Now, the closer two charges are, the stronger the force between them will be. So let's return to our positive and negative charges. When they're far apart, like we show them here, the force between them is relatively weak, as indicated by the short arrows. As we move the charges closer together, the forces get stronger, which we show by the arrows getting longer. Coulomb's law is also quantitative. It relates the force between two objects to their electrical charges. Here's Coulomb's law again. The force is equal to K times Q1 times Q2 over r squared, where Q1 and Q2 are the charges and r is the distance between them. One of the keys to Coulomb's law is that the charges are multiplied together, which means their signs, whether positive, negative, or neutral, also get multiplied. Let's say Q1 is positive, and let's say Q2 is positive as well. Multiplying two positive charges results in a positive force. And when a force is positive, here it means repulsive, pushing the charges away from each other. Now let's suppose Q1 is negative, and that Q2 is also negative. Multiplying two negatives again results in a positive force. So again, Q1 and Q2 will repel. If one of the charges is positive while the other is negative, then their product will also be negative, which means the force is attractive. So multiplying the charges is one key to Coulomb's law. The other key is the r squared in the denominator. Suppose we doubled the distance between two charges. How would the force change? Doubling the distance means we're changing the r to 2r. Squaring 2r gives 4r squared, and we can move the 4 in front of the fraction, keeping it in the denominator. So now we have 1/4 of our original force, back when the distance was r. Doubling the distance results in 1/4 of the force. Similarly, halving the distance would have quadrupled the force. In other words, Coulomb's law is what's known as an inverse square law, like the law of gravity, and so distances are very important.
Okay, as mentioned in the video, Coulomb's law includes a constant value. In the video, he gave that constant value as 9 times 10 to the 9th, and that was just an approximation. For our purposes, we're going to assume K has a value of 8.99 times 10 to the 9th newtons meter squared per Coulomb squared. Okay, so what is this Coulomb unit that we keep mentioning or talking about? A Coulomb is just a unit of charge. Now remember, charge comes from our electrons being transferred from one object to another. To put the unit of Coulomb in perspective, one electron has a value of 1.602 times 10 to the negative 19th coulombs. So to actually get 1 Coulomb of charge, that is a lot of electrons that we're talking about. Typically when we produce charges by rubbing or any kind of friction, they're around the microcoulomb value. So 1 microcoulomb is equal is 10 to the negative 6 coulombs. You will want to write that down and have that number either ingrained in your memory or somewhere where you can easily look it up. Okay, so let's see how Coulomb's law is applied. So we have two positive point charges Q1 a 50 microcoulomb charge to the left and Q2 a 1 microcoulomb charge on the right, and they have a certain distance of 0.03 meters. Since both charges are positive, we know that they're going to experience a repelling force. What I want to know is what is that force that's felt on these two charges. Okay, again, Coulomb's law is represented as force is equal to K times Q1, Q2, all over the distance separating them out. Okay, let's list what we know. We know that K is equal to 8.99 times 10 to the 9th. Q1 is 50 microcoulombs, so times 10 to the negative 6th. Q2 is 1 microcoulomb, so 1 times 10 to the negative 6th. Our length, or our radius, or our distance between them is 0.03 meters. Okay, substituting all those values in gives you a representation that looks like this. Okay, now I want you to practice putting it in your calculator to make sure you're getting your exponents in correctly, make sure you're getting your squared in correctly, because that's where people tend to make the most mistakes. When you type it in and get an answer, you should be getting 500 newtons of force. Okay, going back to that question, which is larger in magnitude, the force that Q1 exerts on Q2 or the force that Q2 exerts on Q1? They're the same thing because those charges are exerting a force on each other equally. Okay, let's complicate the situation a little bit and put 3 charged particles in a line. I want to know what the net force is on particle 3. So I want this guy right here on the end. If we think about what's happening, it's experiencing an attractive force from that positive charge in the middle, but it's also experiencing a repulsive force from charge number 1. So notice how, if I draw my free body diagram on the bottom, the force between charge 3 and charge 2 would cause that negative charge to move to the left. The force between charge 3 and charge 1 would cause charge 3 to move to the right. What I want to do again is find the net force. What I need to do is set up 2 different problems. So I'm going to set up the force between particle 3 and particle 2. We have a value for K. I'm just going to leave it as K for now, but I'll type it in my calculator the way it's supposed to be. Charge number 3 is negative 8 microcoulombs, so times 10 to the negative 6th. Charge 1 is negative 4 microcoulombs, so negative 4 times 10 to the negative 6th. They're separated by a distance of 0.5 meters, so I'm going to take 0.5 squared. When I do that, I get a value of 1.15 newtons. Now what I need to do is find the force between charge 3 and charge 1. We have a value for K. Charge 2 is 3 times 10 to the negative 6 microcoulombs. It's a positive charge. Charge 3 again is negative 4 times 10 to the negative 6 microcoulombs. Those 2 charges are only separated by a distance of 0.2 meters. This time I get a negative value for force. So when I type it in, 0.697 newtons. Okay, I have 2 different force values. To find the net force, I simply add them together. So my net force is equivalent to negative 1.547. That negative lets me know that this is a repulsive force. Okay, please go back and rewatch any part of this video that is unclear to you and come to class ready with questions.